In another series, we built AI agents up from the ground, walking through, in simple terms, how you design an agentic system. We gave a model prompts, handed it tools, wrapped it in memory and guardrails, but through all of it, one thing stayed a given. Jigbox sitting at the center of every diagram labeled the model. We never once asked the most basic question of all. Where did that box come from? Who put the intelligence inside it? And here's the first surprise, the one that reframes everything. Nobody programmed it. There's no giant file of rules somewhere that says how grammar works, or what the capital of France is, or how to write a Python loop. No engineer typed any of that in. The knowledge, the skill, the apparent understanding, none of it was written by a human hand. Instead, the model was grown. It started as a blank slate, billions of numbers set to random noise, knowing absolutely nothing. And then, through a process we're about to walk through in detail, it slowly, automatically grew into something that can write, reason, translate, and code. It's less like building a machine and more like cultivating one. This process is called pre-training. It is, by an enormous margin, the most expensive, most compute-hungry, most consequential step in all of artificial intelligence. It's where the raw intelligence that every one of those agents, tools, and applications quietly depends on actually comes from. And it rests, astonishingly, on a single, almost laughably simple idea. So today we open the box. We're going to follow the whole journey from a pile of raw text and a slate of random numbers, all the way to a model that seems to understand the world. This is a deep one, so we'll take our time and we won't skip the hard parts. Let's begin. Chapter 1, the one big idea. If you remember nothing else from this video, remember this. Underneath all the scale, all the engineering, all the billions of dollars of computation, a language model is trained to do exactly one thing: predict the next word, or more precisely, the next token. That's it. That is the entire objective. Picture it as a game. You take a sentence from somewhere in the training data. The cat sat on the, and you hide the next word. You show the model everything up to that point and you ask it what comes next. The model makes a guess. Then you reveal the real answer, Matt, and you tell the model how wrong it was. Play that game once and nothing happens. Play it a few trillion times and something miraculous does. And the natural reaction is disbelief. How could just predicting the next word possibly produce intelligence? It sounds far too simple, but sit with it for a moment. To predict the next word really well across the entire internet, the model is quietly forced to learn almost everything. To finish the sentence, the Eiffel Tower is located in the city of, it has to learn geography. To finish, the murderer turned out to be the, it has to track a whole plot. To finish a line of code correctly, it has to learn programming. To finish 2 + 2 =, it has to learn arithmetic. Prediction isn't a trivial task in disguise. Doing it well requires a working model of the world, and that is the deep trick at the heart of everything. There's one more beautiful thing about this idea. Notice that we never needed a human to label anything. The correct answer, the real next word, is already sitting right there in the text. The data labels itself. This is called self-supervised learning, and it's the reason we can train on trillions of words. Every sentence ever written is, for free, a ready-made practice question. So the objective is fixed, and it's simple: predict the next token. Everything else in this video, all 15 chapters of it, is just the machinery required to play that one game at an unimaginable scale, and it starts with the raw material, the text itself. Chapter 2, the raw material. If the whole game is predicting the next word in real text, then the text you learn from is everything, and the appetite here is difficult to overstate. Modern models are trained on truly staggering quantities of text, not millions of words, not billions, trillions. Where does it all come from? A huge crawl of the public web, billions of pages, vast digital libraries of books, the entirety of Wikipedia, enormous archives of public code, discussion forums, scientific papers, transcripts. Essentially, a very large fraction of everything humanity has ever written down and put online, swept up into one colossal pile. And the scale is genuinely hard to picture. A large training set might contain 10 trillion words or more. If you tried to read it yourself at a normal reading pace without ever sleeping, it would take you tens of thousands of years to finish. The model effectively reads all of it, many times over, in a matter of weeks. But here's the part that surprises people. It is absolutely not enough to just dump raw internet text into the machine. The internet is full of garbage, spam, broken pages, duplicated text, toxic content, machine-generated nonsense, sheer noise, and there's an iron law in this field. Garbage in, garbage out, train on junk, and you get a junk model. So an enormous, underappreciated amount of work goes into cleaning that pile before a single training step happens, filtering out the spam and the toxicity, removing near-duplicate documents so the model doesn't just memorize things it saw 1,000 times, stripping boilerplate. Carefully balancing the mixture, how much code, how much prose, how many languages. The quality and the composition of this data shapes the final model's mind as much as anything else that follows. So we have our raw material, a colossal, painstakingly cleaned mountain of human text, but a neural network doesn't actually read words the way you and I do. Before it can learn from any of this, the text has to be turned into something a machine can work with, numbers. And that transformation is more subtle than it sounds. Chapter 3: Tokenization. A neural network is, at its core, a giant machine for doing arithmetic. It only understands numbers. So the very first thing we must do is convert our ocean of text into numbers, and the unit we chop text into has a name, a token. Your first instinct might be to just use words, one number for each word, but that turns out to work badly. There are millions of distinct words once you count every name, typo, and technical term. And it falls apart completely on a word the model has never seen before, or on languages that don't neatly split on spaces. The opposite extreme is to use single characters, just 26 letters and some punctuation. That never runs out of vocabulary, but it goes too far the other way. Now the model has to work incredibly hard to build up any meaning, letter by painstaking letter, and sequences become enormously long. So in practice we land in the middle with subword tokens. Common words like there and cat get their own single token, but rarer words get broken into meaningful chunks. Tokenization might become tokenization. Unbelievable might become unbelievable. The vocabulary settles at a sweet spot, typically somewhere around 50 to 100,000 tokens, big enough to be efficient, small enough to be manageable, and it can spell out absolutely anything by combining pieces. Every token in that fixed vocabulary is simply assigned a number, an ID. The might be token 411, cat might be token 9,000, so a sentence becomes a list of integers. The text, the whole of human writing, is now a river of numbers flowing into the machine. When you hear their model has a context window of, say, 100,000 tokens, this is exactly what's being counted, these little pieces. But a token ID on its own is just an arbitrary label. The number 9,000 tells the model nothing about what a cat actually is, or that it's similar to a dog and quite different from a democracy. For the model to reason, these bare numbers have to be given meaning. And that is the job of the next, genuinely beautiful, step. Chapter 4: Embeddings and the Shape of Meaning. We have tokens, but they're just ID numbers, meaningless labels. The next step turns each one into something rich. We replace every token ID with a long list of numbers, a vector, and this vector is called an embedding. So the token for cat isn't the number 9,000 anymore. It becomes a list of maybe a few thousand numbers, a point floating in a space with thousands of dimensions. Now, we can't picture thousands of dimensions, but the intuition works perfectly in the 2 dimensions we can draw. Think of a vast map where every token in the vocabulary sits at some location. And the magic is what the training process does to that map. It arranges it so that meaning becomes geometry. Tokens with similar meanings drift close together. Cat, dog, and hamster end up clustered in one neighborhood. King, queen, and prince in another. Words about cooking gather over here, words about finance over there. Distance on this map becomes a measure of similarity. Closeness means relatedness. This is the meaning space we first met, from a completely different angle, in the video on retrieval. And here's the crucial point. Nobody draws this map by hand. Nobody decides where cat should go. The positions start as pure random noise, every token scattered meaninglessly, and they are learned, nudged into place automatically by the very same next token prediction game. The model discovers entirely on its own that cat and dog belong near each other, purely because they get used in similar ways across the data. It goes deeper still, and this is genuinely one of the most beautiful results in the field. Directions in this space come to carry meaning too. There's a direction you can move that roughly corresponds to making a word plural, another for changing the tense of a verb. Famously, if you take the point for king, subtract the direction for man, and add the direction for woman, you land remarkably close to the point for queen. The model has learned the concept of royalty and the concept of gender as directions you can travel, meaning made into arithmetic. So now each token is a rich vector in a meaningful space. We've turned dead labels into living meaning, but so far, each token's meaning stands alone. The word bank looks the same whether we're talking about a river or about money. To resolve that, the model has to let tokens look at each other and share context, and that happens inside the machine itself. Chapter 5, Inside the Box. From altitude, we now have a sequence of embeddings flowing in. This is where the real engine sits, the architecture that does the thinking. Almost every modern language model is built on one design, and you've heard its name, the transformer. At the highest level, a transformer is a tall stack of identical layers. The embeddings enter at the bottom and they flow upward, passing through layer after layer, sometimes dozens, sometimes over 100 of them. At each layer, the representation of every token gets refined a little, enriched, updated. By the time the sequence reaches the top, each token's vector has been transformed from its plain starting meaning into something deeply contextual. And inside each of those layers sit two main operations, working in turn. The first lets the tokens communicate with each other. It's the step where the word bank finally gets to look around, notice the nearby word river, and adjust its own meaning accordingly. This communication step is called attention. The second operation then takes each token on its own and does some private computation on it, a little burst of thinking. This part is called the feed-forward network. Now, attention is the single most important idea in modern AI, and it is subtle enough and important enough that it deserves its own dedicated video, which is coming up next. So here, I'm going to ask you to hold just the intuition. Attention is how tokens share information and build context. Feed-forward is how each token then thinks. Layers stack these two over and over, and depth is where sophistication comes from. That intuition is all we need for pre-training. One more mental image worth carrying. Picture a central highway of information running up through all the layers, carrying each token's evolving meaning. Every layer doesn't rebuild that meaning from scratch. It reads from the highway, computes a small improvement, and adds that improvement back on. Layer by layer, each token's representation accumulates richer and richer understanding, like edits building up on a shared document. It arrives at the top, carrying the weight of everything the model has noticed about it. So the sequence enters as plain embeddings and climbs the stack, every token gathering context and refinement as it rises. At the very top, out comes a final, deeply informed vector for each position, and now the model has to do the one thing it was built for. Turn that into an actual prediction of the next token. Chapter 6, Making the Prediction. The sequence has climbed all the way up the transformer. For the final position, the one right before the word we're trying to predict, we now hold a single rich vector, packed with context. The model's last job is to turn that vector into a guess about what comes next, and the shape of that guess is important. First, that final vector gets compared against every single token in the vocabulary. This produces a raw score for each possible next token, a number saying, roughly, how strongly the model favors this one. So for a vocabulary of 50,000 tokens, we get 50,000 raw scores. These raw, unnormalized scores have a name in the field. They're called logits. And notice something crucial here. The model's output is not a word, it's not a single answer. It is a score for every token at once, a giant list of preferences across the whole vocabulary. To turn that into something we can actually use and learn from, we need to convert those raw scores into proper probabilities. Numbers between 0 and 1 that all add up to 1. The function that does this is called the softmax, and its job is intuitive even if the formula looks fancy. Take all the raw scores and turn them into a clean probability distribution where the biggest scores get the biggest probabilities, but nothing ever drops to exactly 0. The formula is this: for each token you take E, the mathematical constant, raised to the power of that token's score, and then you divide by the sum of that same quantity across all tokens. The exponential exaggerates the differences, so the leader pulls ahead, and dividing by the total forces everything to sum neatly to 1. So the true output of a language model at every step is this: a probability distribution over the entire vocabulary, mat 61%, floor 18%, roof 9%, and a tiny sliver of probability spread across all 50,000 other tokens, including the absurd ones. The model isn't certain, it's expressing with numbers exactly how plausible it finds every possible continuation. To actually generate text, you then just sample a token from this distribution and repeat, but for training, this full distribution is precisely what we need. So the model has committed to a guess, a confident probability distribution over what comes next. Now comes the moment of truth. We know the real next token because it was sitting in the training data all along. So how do we measure just how wrong or right the model's guess was? For that, we need the loss. Chapter 7, Learning by Being Wrong. Here's the beating heart of training. The model has produced a probability distribution over the next token. We know the true answer. Now we need a single number that captures how bad the model's prediction was, a score of wrongness. That number is called the loss. And the idea behind it is elegant. We look at how much probability the model assigned to the correct token, the one that actually came next. If the model was confident and right, it gave the true token a high probability, and the loss should be low. If it was confident and wrong, it gave the true token a low probability, and the loss should be high. The loss punishes confident mistakes and rewards confident correctness. The specific measure used is called cross-entropy loss, and for next token prediction it takes a beautifully simple form. The loss is just the negative logarithm of the probability the model gave to the true token. Let's write it. The loss script L equals minus log p, where p is the probability assigned to the correct next word. That single, compact expression is what drives the training of every large language model on Earth. Let's feel why that formula works, because it's lovely. The logarithm of 1 is 0, so if the model gave the true token a probability of 1, perfect confidence, and it was right, the loss is minus log of 1, which is exactly 0. No penalty, perfect. But as the probability it gave the true token shrinks toward 0, the log dives toward negative infinity, and the negative flips it to a huge positive number. So being confidently wrong, giving the right answer almost no probability, is punished enormously. You can think of the loss as a measure of the model's surprise. A low loss means it saw the real word coming. A high loss means the real word shocked it. In practice, we don't just do this for one word. We do it across a whole batch of text at once, computing this surprise for every predicted token and averaging it all into one overall number. That single averaged number is the model's report card for this moment. And the entire goal of training, the only goal, is to make that number, that average surprise, as small as possible. Everything now hinges on one question. Given that we have a number telling us how wrong we are, how do we actually change the model to become less wrong? We have a score of wrongness and billions of numbers inside the model that produced it. Somewhere in those billions of knobs is the reason the guess was off. The next step is the true engine of learning. Figuring out how to turn every one of those knobs, just slightly, in the direction that shrinks the loss. Chapter 8, the update where learning actually happens. Let's be concrete about what's really inside the model. It's numbers, billions of them. These numbers are called the parameters or the weights, and they are the knobs that control everything the model does. When we say a model has 70 billion parameters, we mean it has 70 billion of these little adjustable numbers. At the very start of training, every single one of them is set randomly. The model is pure noise, it knows nothing. So picture a mixing board with billions of knobs. Learning is nothing more and nothing less than finding the right setting for every one of those knobs so that the model's predictions come out good. That's the whole game. The question is just, when the loss is high, which knobs do we turn and in which direction? And this is where calculus gives us something almost magical, called the gradient. For every single one of those billions of knobs, we can compute a number that answers a precise question. If I nudge this particular knob up a tiny bit, does the loss go up or down, and by how much? The gradient is the giant collection of all those answers, one for every parameter. It's an arrow in billion-dimensional space that points in the exact direction of steepest increase in the loss. But we don't want to increase the loss, we want to decrease it, so we do the obvious thing. We step in the opposite direction of the gradient. We nudge every knob a tiny amount the way that makes the loss go down. This is called gradient descent, and the image is perfect. Imagine standing on a foggy hillside wanting to reach the valley. You can't see far, but you can feel which way is downhill under your feet, so you take a small step downhill. Then you feel again and step again. Gradient descent is exactly that, in a landscape with billions of dimensions. We can write the update in a single line, and it's worth seeing because this one rule, repeated, is how every model learns. The new parameters equal the old parameters, minus a small number eta, times the gradient of the loss. Theta becomes theta minus eta times the gradient. Theta is all the knobs, the gradient points uphill, so we subtract it to go downhill. And eta, that small number, is the learning rate. It controls the size of each step. Too large and you leap wildly past the valley. Too small and it takes forever. Choosing it well is one of the quiet arts of the whole endeavor. Now, how do we actually compute that gradient for billions of parameters efficiently? The answer is a famous algorithm called backpropagation. The intuition is that it works backward. It starts at the loss, at the model's final mistake, and it flows the blame backward through the network, layer by layer, using the chain rule from calculus to figure out exactly how much each knob, all the way back down, contributed to the error. We won't derive it here, but that's the idea. Backpropagation assigns responsibility. Gradient descent acts on it. And that's it, that's the atom of learning. Predict, measure the loss, compute the gradient by backpropagation, and nudge every knob a hair downhill. One turn of that cycle barely changes anything. The model is still almost pure noise, but we are not going to do it once. We are going to do it an astronomical number of times. Chapter 9, The Loop at Scale. We now have the complete recipe for a single step of learning. Take some text, predict the next tokens. Measure the loss, the surprise, compute the gradients, nudge the billions of knobs slightly downhill. That's one step. Pre-training is just this exact step, repeated, until the model is astonishingly good, but the numbers involved are what make it almost incomprehensible. First, we don't feed the model one sentence at a time. That would be hopelessly slow. Instead, we process huge batches, thousands and thousands of chunks of text simultaneously, computing the loss and the gradients across all of them at once before making a single, well-averaged update. This is why the hardware matters so much. Modern chips, the ones you hear called GPUs, are built precisely to do this kind of massive, parallel arithmetic. And then we repeat and repeat. The model works its way through the entire ocean of training data, often more than once. We're talking about hundreds of thousands, even millions of these update steps. Trillions upon trillions of individual next token predictions, each one contributing a tiny nudge to the knobs. No single step teaches the model much. It's the sheer, relentless accumulation of trillions of tiny corrections that slowly sculpts random noise into intelligence. And the beautiful thing is that you can watch it happen through that one number, the loss. At the very start, it's high. The model is guessing essentially at random, constantly surprised by every word. And as the steps tick by into the millions, the loss curve slides downward. Steeply at first, as the model rapidly learns the easy patterns, grammar, common words. Then more slowly, grinding lower and lower as it picks up the subtle, hard-won stuff, facts, reasoning, style. That descending curve is, quite literally, the sound of a mind being formed. And none of this is cheap. Training a frontier model means running thousands of these specialized chips in parallel continuously for weeks or even months. It consumes staggering amounts of electricity and costs tens, sometimes hundreds, of millions of dollars in a single training run. This is why only a handful of organizations in the world can currently train the very largest models from scratch. Pre-training is, without exaggeration, one of the most expensive computations humanity has ever performed. So the loop is simple, but the scale is titanic, which raises the obvious and deeply important question: why so big? Why trillions of words and billions of parameters and months of compute? Is all that scale really necessary? The answer to that turns out to be one of the most important and most surprising discoveries in the entire field. Chapter 10: Scale is the secret. For a long time, people assumed that building better AI would mostly be about clever designs, ingenious new algorithms, handcrafted insights, and those things do matter. But the single most important lesson of the last several years has been humbler and stranger than anyone expected. To a remarkable degree, you just make it bigger. There are really three dials you can turn. The first is the number of parameters, the count of knobs, how big the model is. The second is the amount of data, how many tokens it trains on. And the third is compute, how much total calculation you pour in. Turn all three up together and the model gets better. Reliably, predictably, almost boringly so. And that predictability is itself a profound discovery. It's captured in what are called the scaling laws. When researchers plotted model performance against scale, they didn't find a mess. They found smooth, clean curves. Curves so regular that you can now estimate in advance, before spending a single dollar, roughly how good a model will be if you make it a certain size and train it on a certain amount of data. Intelligence, it turns out, responds to scale in a way you can put on a graph and forecast. This has been called the bitter lesson. Bitter because it's a little deflating for human ingenuity. Across decades of AI research, again and again, the elegant, clever, hand-designed approaches were eventually overtaken by simple, general methods that could just absorb more computation and more data. The lesson history keeps teaching is that general methods that scale tend to win, in the end, over clever methods that don't. Pre-training a giant transformer on the whole internet is that lesson, taken to its logical extreme. It's not entirely mindless, of course. There's real skill in balancing the dials. Spend too much on model size and not enough on data, and you waste the parameters. Get the ratio right, matching the amount of data to the size of the model, and you extract far more intelligence from the same budget. But the headline remains one of the defining facts of our moment. A huge fraction of the progress you've witnessed in AI came not from a new idea, but from turning these dials up and up and up. So we scale because scale works with an almost eerie reliability, but this leaves us with the deepest mystery of all. We only ever train the thing to predict the next word. So where do all the other abilities come from? The reasoning, the translation, the coding, the conversation. Nobody trained it to do any of those specifically, and yet there they are. Chapter 11: What emerges? This is the part that still genuinely astonishes the researchers who build these systems. We set out to do one narrow thing: predict the next token. We never wrote a lesson on grammar, never taught a translation rule, never explained what a poem is or how to solve an equation. And yet a well-trained model can do all of these and far more. These abilities were never programmed in, they emerged. And once you sit with the core idea, you can start to see why. Remember, to predict the next word really, really well, across the sheer variety of everything humans have ever written, the model is quietly forced to learn the underlying structure that generates that text. It can't fake it at this scale. To reliably continue text about the physical world, some internal sense of how the world works has to form. This is often called a world model. Understanding, it seems, is what prediction turns into when you push it hard enough. So capabilities appear as side effects. Feed it enough English and French sitting side by side, and the ability to translate falls out because translation helps it predict. Feed it enough code and it learns to program. Feed it enough worked examples and a capacity for step-by-step reasoning appears. Feed it enough dialogue and it can hold a conversation. None of these were goals. All of them were simply useful for the one goal it did have: getting the next token right. Stranger still, some of these abilities appear suddenly. Researchers have watched capabilities that were essentially absent in a smaller model switch on, almost like a light, once the model crosses some threshold of scale. A certain kind of reasoning that a small model simply cannot do becomes, past a certain size, something the model just does. These are sometimes called emergent abilities, and their unpredictability is one of the most fascinating and slightly unnerving features of the whole enterprise. You don't always know what a bigger model will be able to do until you build it and look. This completely reframes what a language model even is. It is not a database of facts that got looked up. It is not a search engine. It is a system that, in the relentless pursuit of predicting text, was forced to compress the patterns of human knowledge and reasoning into its billions of weights. The intelligence isn't stored in there like books on a shelf. It's baked into the very structure that makes the predictions, and that is a genuinely new kind of artifact in the world. So out of a simple objective pursued at enormous scale, something rich and general emerges. But before we get carried away, we have to be precise about what, exactly, we've made at the end of pre-training, because it is powerful, yes. But it is also, in a very specific and important way, not yet the helpful assistant you're used to talking to. Chapter 12, what a base model actually is. At the end of pre-training, we have what's called a base model, or a foundation model. It is the raw, distilled result of all that computation. And it's essential to understand its true nature, because it is not what you interact with when you open a chatbot, not yet. A base model is, at its core, one thing, a document completer. Its entire being is bent toward continuing text in a way that's plausible, given everything it absorbed. That's all it knows how to do. It doesn't fundamentally think of itself as an assistant or as anything at all. It just takes whatever text you give it and relentlessly predicts what would naturally come next. This makes a raw base model behave in ways that feel strange if you're expecting a helpful assistant. Ask it a question and it might not answer it. It might instead continue it with more questions, because in its training data, questions are often followed by more questions in a list. Give it an instruction and it might just rephrase it or ignore it and carry on with some plausible seeming text. It's not being difficult, it's doing precisely what it was trained to do, complete the document. It has no instinct yet to be helpful. And yet, make no mistake, this raw base model is where essentially all the capability lies. All the knowledge, the reasoning, the language, the coding ability, the latent understanding of the world, it's all in there already, fully formed at the end of pre-training. The base model is a vast reservoir of raw intelligence. It's just intelligence without direction. Immense power with no steering wheel and no sense of purpose. And this is the exact gap that the next video is all about. Taking this brilliant, knowledgeable but wild and unsteerable base model and shaping it gently into the helpful, honest, safe assistant you actually want to talk to. That process is called fine-tuning, and it's a fascinating story in its own right, but it can only shape what pre-training has already grown. The raw material has to exist first. So the base model is a genius with no manners and no mission. Before we close, though, honesty demands that we talk about the flip side. Because everything we've described, this process of absorbing the entire internet through prediction, doesn't just grant abilities. It also bakes in some deep and permanent limitations. Chapter 13, what pre-training bakes in. The way a model is pre-trained doesn't just determine what it can do, it determines its flaws too. And understanding these isn't pessimism, it's essential. Nearly every well-known weakness of language models traces directly back to something about this process. Let's name the big ones. First, the knowledge cutoff. A base model's knowledge is frozen at the moment its training data was collected. It learned from a snapshot of the world taken at a particular time, and then that learning stopped, so it simply does not know about anything that happened afterward. Its knowledge has a hard expiry date baked in on the day training ended. This, by the way, is a huge part of why retrieval from the RAG video matters so much. It's how you hand a frozen model fresh information. Second, bias. The model learns from human text, and human text is full of human biases, stereotypes, and imbalances, along with all its wisdom. The model absorbs all of it indiscriminately. It doesn't judge the data, it just models it. So the biases present in what humanity has written online end up, to some degree, reflected in the model. And confronting that is an active, difficult, and deeply important area of work. Third, and most fundamentally, hallucination. Remember what the model was optimized for, not truth, plausibility. Its entire training pushed it to produce text that seems likely, that flows naturally, that fits. And most of the time, plausible and true happily coincide, but not always. When the model doesn't actually know something, it doesn't fall silent. It generates the most plausible sounding continuation it can, which may be a confident, fluent, complete fabrication. Hallucination isn't a bug that slipped in. It's a direct, unavoidable shadow of an objective that rewarded plausibility, never verified truth. And finally, the practical shadows, the staggering financial and energy cost we discussed, which concentrates the power to build these models in very few hands, the colossal, hard-to-audit datasets with all the thorny questions they raise about what went in and who it belonged to. These aren't footnotes, they're real consequences of doing intelligence this way, and they belong in any honest account of it. None of this is a reason to dismiss what pre-training achieves, which remains genuinely astonishing. But a clear-eyed understanding means holding both truths at once, immense, emergent capability and deep, structural limitations arising from the very same process. With that balance in mind, let's step all the way back and take in the whole journey we've traveled. Chapter 14, The Complete Picture. Let's retrace the entire path from nothing to a mind. We started with a colossal, carefully cleaned ocean of human text. We chopped it into tokens and turned those tokens into rich vectors in a meaningful space. We fed them up through a deep stack of transformer layers, where attention let tokens share context and feed-forward layers did the thinking. At the top, the model produced a probability distribution over the next token via the softmax. We measured its wrongness with the cross-entropy loss, the negative log probability of the true token, its surprise. We used backpropagation to compute the gradient, and gradient descent to nudge billions of parameters a hair downhill. And then we did that not once but trillions of times, a scale so vast it costs a fortune, until a smooth descending loss curve marked the slow transformation of random noise into structured knowledge. And out of that single, simple, objective, general intelligence emerged. And here is the one idea to carry away from all of it. Intelligence, at least this kind of it, was not designed. It was grown automatically from prediction and scale. Nobody wrote the knowledge down. The model was pointed at the sum of human writing, told to guess the next word, 1,000,000,000 times over, and it grew a compressed, working model of the world as the only way to succeed at that impossible game. That is a genuinely profound thing to have discovered about the nature of learning itself. But we're left holding a base model, a reservoir of raw, formless intelligence, a brilliant document completer that doesn't yet know it's supposed to help you. In the next video, we take exactly this model and we sculpt it. We teach it to follow instructions, to be helpful, honest, and harmless through supervised fine-tuning and learning from human feedback. If pre-training grew the mind, fine-tuning gives it a purpose. That's where we go next. Thank you sincerely for staying with me through this deep one. This is the foundation that everything else is quietly standing on. Every agent, every tool, every prompt from that other series rests on the raw intelligence grown right here. If it made the origin of these systems finally click, give it a like, it genuinely helps, and subscribe because there is more to come. We're building AI up from the ground, one blueprint at a time. I'll see you in the next one.